Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 211 Classical Mechanics. It is the 14th lecture of this course and the topic is motion under constraint. First, I will give the learning objectives. At the end of this presentation, the student will understand the motion of particles under constraints, and they will be able to understand the various forms of the constraint forces based on mathematical descriptions. In this course, we are following the book Classical Mechanics by Goldstein, Paul and Safko, 3rd edition. In this lecture, I have taken some of the illustrations from this book. In the first part of this course, we have gone through the review of the Newtonian mechanics, where we have solved the equation of motion for various problems in obtaining the expressions for the acceleration, velocity, and position vectors. Now, in doing so, we have to solve the set of differential equations, since those equation of motion is nothing but set of differential equations. Now, in most of the practical problems, we have systems under constraint. So in those situations, in order to solve those set of equations that I told you, the equation of motion for a system of n particles, we have to impose certain restrictions on the position and velocities of the particles of the system. You will see those restrictions and constraint in this lecture. So in such situation, the descriptions of the Newtonian mechanics in solving those set of equations for obtaining the expressions for the velocity, acceleration, or position vector, or in another word, describing the motion of those systems under constraint, the mathematics is complicated. So we need to switch to the energy descriptions. In this lecture, we will be trying to describe these constraints, which are just restrictions on the position and velocity of the particles of the system, and also we need to see how the Newtonian mechanics is difficult in describing those systems, and there is an alternate mechanics which we will be trying to introduce in this lecture as well. So such restrictions, or we can say such geometrical or kinematical restrictions on the motion of particle or system of particles, are called constraints. So we can have these various examples, and we will see the mathematical forms of these constraint equations in this lecture as well. For example, the motion of a rigid body restricted by the condition that the distance between any of its two particles remains unchanged. We'll see this in this lecture as well. Also, the beats of an abacus constrained to one-dimensional motion by the supporting wire. We'll also see the two situations where in the first situation the string is moving and the beat is also moving along that string, and in the another case we'll see the stationary string over which the beat is moving. Also, another example that we will see in this lecture that is related with the constraint motion, that is the gas molecules within a container restricted by the wall of the vessel. So these are the various examples of the constraint motion, or we can say constraint systems, where the solution of the differential equation based on the Newtonian mechanics is somehow difficult, because we will see in this lecture that due to constraint, unknown forces arises which are not known in advance. So first we need to solve those or eliminate from this set of equations, and then we will be obtaining the dynamical parameter, which are acceleration, position, and velocity. So before moving towards those problems, we need to uh, see the classifications of the constraints. So constraints can be holonomic if the condition of the constraint connecting the coordinates of the particle, and also in some form of the constraint time, that can be expressed in the form of equation. So we will see on the coming slide the equation of constraint for various systems. So if that condition of the constraint is expressible in the form of an equation, so those constraints are holonomic constraint. Out of the holonomic constraint, if that constraint is time dependent, so that those constraints are scleronomic constraints. So constraints which are independent of time are called scleronomic constraint. For example, bead sliding on a rigid curve, wire fixed in space. So constraints which are independent of time, that is, we have this function which does not appear this time explicitly. So those are scleronomic constraints. Now, also those constraints which can be expressed in the form of this equation, but also it depends upon time. So those are rheonomic constraints. So we'll also see the various mathematical forms of these constraints. For example, bead sliding on a rigid curve while moving in some prescribed fashion. So in this lecture we'll be covering both of these situations, that is a bead sliding on a curve fixed in space, and also moving wire as well. So one is the scleronomic and the other one is rheonomic constraints. Constraint, this is another example of the time dependent constraint. That is, if we construct a simple pendulum whose length changes with time. So those situations, the constraint equation explicitly depends upon time. So that is also a situation of rheonomic constraint. The non-holonomic constraint are those constraints where the equation of the constraint cannot be expressed with the help of this equation, but such constraints are expressed in terms of inequalities. So we will see the examples of the non-holonomic constraint in this lecture as well. So based on the various classification of the constraint, here we will see various examples of the constraint system. So the first one is the motion of a particle on a circular path. So here we have a particle which is moving on this circular orbit having radius a. So this object is constrained to move along this path. So that is that particle is bound to move in a plane where the equation of constraint can be expressed as x square plus y square equal to a square, where a is the radius of the circular orbit. Now, from this equation of constraint, we can have x is equal to a cos theta and y is equal to a sin theta. And the theta in this case ranges from 0 to 2 pi. So the constraint in this example is holonomic. Since the equation of constraint can be expressed in the form of an equation which is connecting the configuration and also the time. But since in this equation of constraint the time is not explicit here, so we can say that out of the holonomic constraint, this is an example of the scleronomic. Since I told you that scleronomic constraints are the scleronomic constraints are independent of time. So in such situation we will see various examples that describing the motion of such system is easy to use the energy descriptions. Now in the classifications of the constraint, here we will be going through another situation where the motion of a bead. So let's say we have a wire over which this bead is moving. So if we want to describe it, so we need to have our coordinate system. So let's say this is y and this is x. So in this situation, the equation of constraint is y is equal to x time tangent theta. Now this is again a holonomic constraint, and since this is time independent, the equation of constraint is time independent, so out of the holonomic constraint, this is in the scleronomic constraint. Now in the last part of this lecture, I will be comparing the equation of motion for the motion of this bead along this wire that we will be obtaining with the help of energy description, and we will be comparing that equation of motion with the Newtonian approach, just to see how simple the energy mechanism is once constraints are introduced in the system. Now the same motion of bead can be rheonomic if that string is moving with some velocity. So for that situation, let we have the coordinate axis, and let at any time t it is here, z sine theta, and that system is not stationary but rather moving with the velocity v parallel to the x-axis. So let that system is somewhere here at t is equal to 0, and when t is equal to t, it covered that distance vt. So just to write the same equation of constraint for this system where the string is moving with respect to x. So now the equation of constraint will be y equal to x minus vt times tangent theta. So the same holonomic constraint is now rheonomic, since we have that time factor now. So this time factor is there explicitly here, so we can classify this kind of constraint as the rheonomic constraints. So in the classification of the constraint, here we'll go through another example, that is a bouncing ball, and this is a situation of the non-holonomic constraint. For example, if we just want to configure this bouncing ball such that it will be having a coordinate x, y, z, and let this is the z-axis, this is say y, and this is x. So we can say that this ball is bouncing off xy plane. Now this ball is bouncing off xy plane, so the constraint is that z, which is the height of this ball, will satisfy this inequality. So since the equation of constraint is expressed in terms of inequality, so we can say that this is non-holonomic constraint. So now we want to see another examples of the constraint, and that is the gas molecules inside a container. So we have this container of let's say side L, that is, this is a cubical container in which we have these gas molecules. So if we want to write the configuration for this gas molecule, let's say this is the ith molecules of this gas, so this configuration will be xi, yi, and zi, that is the respective position vectors along the three coordinates, where since we have in this container let total number of gas molecules of n, so then we can write this n equals from 1 to n. So we have choose just the nth particle. So the equation of constraint will be, that is this xi, yi, and zi is bound inside the container. So once this is constrained to move inside this vessel of side L, so the configuration of this ith particle will satisfy this equation. Again, this is expressed in terms of inequality, so this is a non-holonomic constraint. Now we need to see another example, that is a spherical pendulum, where we have a mass which is connected to a rigid rod of length L, and that is fixed from this point. So in such situation, the equation of constraint is x square plus y square plus z square equal to L square. Another thing is that if we have two masses, connected through a rigid rod of length d, which is known as a dumbbell. So for such system, let's say the mass 1 is having configuration x1 y1 and the mass 2 is having configuration x2 y2. So in this case, the equation of constraint will be x1 minus x2 whole square plus y1 minus y2 whole square equal to d square. So in both of these examples, the equation of constraints are expressed in terms of an equation. So they are holonomic constraint. Before we move forward to discuss the motion of system under constraint, we need to discuss or relate the degrees of freedom with the introduction of constraints. So let we have an object which is moving in space such that x, y, z is the configuration. So we have one particle system. So for that we required 3 independent coordinates. So it is having 3 degrees of freedom. Now if it is compelled to move on a surface which is bounded by x and y, such that the object is constrained to move along the z-axis. So in this situation, again we have one particle and the degrees of freedom are now 2. Now the same object is compelled to move along this x-axis, that is, now it is compelled to move on a straight wire, and the same one particle is now having 1 degrees of freedom. Now, so we can see that when constraints are introduced, the degrees of freedom reduces. So in general term, if we have n number of particles, a system of n particles, so we required, if we have n particles, so for that we required 3n number of independent coordinates, and let the number of constraint are k. So the general way to describe the degrees of freedom with respect to the constraint is 3n minus k. So one can verify this situation with the help of this general expression, such that if n is 1, that is, we have one particle system, so this will be 3 minus k, and let we have constraint, the object is constrained to move on a straight wire, and it is constrained not to move on y and z, so then k will be equal to 2 and we will be having 1 degrees of freedom. So from this discussion we can conclude that once constraints are introduced, the number of the degrees of freedom, or we can say the number of independent ways in which a system can act reduces. So constraint reduces the freedom of the particles, we can say. Now, after the classifications of the constraint and the discussion that constraints restricts the motion of particles, or we can say the degrees of freedom. Now we'll be solving the equation motion for a system of constraints. For example, we have discussed the motion of a beat and the equation of constraint for the beat motion on a wire which is stationary. So we'll be trying to compare the equation of motion obtained through the Newtonian mechanics and then based on the energy descriptions. So here, if we draw the diagram of this beat, let's say this beat is moving along this wire, and as I told you, once constraints are introduced, unknown forces arises. So in this case, the normal force is there, which is and also we have the weight of this beat. So if we want to solve this motion under the Newtonian mechanics, so we need to write the equation of motion along the respective axes, so that this mx double dot is equal to minus n sine theta, which is responsible for the motion or the component of the normal force, and also my double dot equal to n cos theta minus mg. Now we have two coordinates. If we discuss this situation with respect to the motion, so we have this unknown x double dot and y double dot, the acceleration along the respective axes, but we have also an unknown, which is the constraint force. This is the normal force. So constraint forces arises once the system is bound to move on this string. So once this is connected to this wire, so that the force arises which is unknown in advance. So first, if we want to solve these two expressions, we need to eliminate n from this two expression. So as I told you, constraint systems give rise to unknown forces, which are known as constraint forces. Now the equation of constraint that we have discussed previously is equal to y is equal to x tangent theta. So with this equation, this is a holonomic constraint and this is time independent. So if we make a double dot of this constraint equation and then using here in the above system of equation, we can obtain the x double dot, which is the acceleration of this beat, that is given by minus g sine theta and cos theta. So from this short example, we can say that once the system is constrained, unknown forces arises which are not known in advance. So first we need to eliminate from the system to describe the motion of that object. So we can say that while solving the systems under constraint through the Newtonian mechanics, we have two difficulties in describing the particles. The first one is the forces of constraint arises which are not known in advance. So first we need to eliminate from the system. And also the number of independent ways in which system can act reduces, that is the number of independent coordinates reduces. As we have discussed on the previous slide, how constraints reduce the degrees of freedom. And from this discussion, it is clear that in this example, the constraint force is the normal force. So the same expression, or we can say the same equation of motion, can be obtained with the help of energy descriptions. Now, That descriptions can be applied to the same situation now. Since this energy description will be talking more in the coming lectures, that is, the Lagrangian mechanics is based on the D'Alembert principle, and over there we'll discuss that these unknown forces, which are the constraint forces, and in this example the constraint force is the normal force, and this normal force is always perpendicular to the motion of the object, since the object is moving along this string, so that this is perpendicular to dr, so that this will not contribute to the work done. That is, the constraint forces do not contribute to the work done. So in total we have two forces. One is the mg, which is the conservative force, and the other one is the normal force, which do not contribute to the work done because of the 90-degree angle between the motion, the direction of motion, and the direction of the force. So with the two force system, it reduces to the conservative form, that is mx dot square plus this is the kinetic energy and this is the potential energy, equal to the constant. So in this way, through the energy description, we can eliminate the discussion of the constraint forces. In this example, as I told you, normal force is the constraint force, so that can be eliminated once we adopt to the energy description, which is a handy tool to describe system under constraint. So the equation of constraint is the same, y is equal to x tangent theta. That can be used to find out the parameters in the energy expression. So if we dot this thing, that is differentiating with respect to time, we will be getting x dot tangent theta. Now that value of y dot and y can be used in this expression such that this is the same and this is half m, and instead of y dot square we have x dot tangent theta whole square, and we have mg times x tangent theta equals to constant. So here if we make a common of half mx dot square from the first two expressions, so we'll be left with 1 plus tangent square theta, and this is the same. So we know that 1 plus tangent square theta is equal to secant square theta, and the rest of the equation is the same. Now if we dot this equation with respect to time, so that this constant, the derivative of this constant with respect to time will be 0, and we will be left with these two terms, so that if we solve these things for x double dot, such that this x dot will be cancelled out, this m will be cancelled out, and we'll be left with the same expression that we have derived on the previous slide through the Newtonian mechanics. If you remember, there we have to deal with the normal force as well, and we need to eliminate from the system of equations, and then we'll be arriving at the equation of motion. So the same can be done with the help of this energy conservation, since the contribution of the normal force towards the work done is 0. So we can solve a complicated problem, or we can say a more realistic system, which are constraint systems, with the help of energy descriptions rather easily as compared to the Newtonian descriptions. So with this, I thank you for your time.